So hello everyone, welcome to the October LINCC Tech Talk. My name is Mi Dai, I'm the host today, and I'm a LINCC Framework project scientist at University of Pittsburgh. LINCC Tech Talk include presentations and demonstrations that showcase work done by the broader roving software and archives community with the goal of further enabling LSST science. Unlike traditional talks you might hear at a conference, Tech Talks highlight the technical aspects of the work being done. We hope these talks provide a useful forum for a range of groups and authors to present, learn about, and discuss efforts of interest in the analysis of LSD data. LINCC Tech Talks are delivered virtually every second Thursday of the month at 10 a.m. Pacific. Today, our speaker is Emilio Donoso. He is going to talk to us about enabling massive correlation functions in the LST area, which is a work from the recently completed LINCC Frameworks Incubator program. Emilio is a staff researcher for the National Scientific and Technical Research Council in Argentina and a professor at National University of San Juan. His research is focused on extragalactic astronomy, studying the evolution and properties of galaxy populations observed by large astronomical surveys. Please ask questions in Zoom or in the LINCC Tech Talk channel. On Zoom, you can type question in the chat or raise your hand. As a friendly reminder, these talks are being recorded and they'll be posted on our YouTube channel later. With that, Emilio, please take it away.
All right. Thank you, Mi. Thank you very much. And thank you all the people present here for giving me the opportunity to present this talk. So let me share my screen. There it is. Hope you can see it. There. Okay. As Mi said, this talk is about the work we have done within the LINCC Frameworks Incubator program. This is a project that we started a few months ago. The idea here is to enable the computation of correlation functions at a massive scale, massive like LSST scales. This is what I mean, the end goal of this. So let me set briefly here a small agenda. So sorry. There. First, I will give you a small introduction to the area. So what is this business of correlations? I will talk about the precursor data set that we downloaded. This is a hypersuprancom super strategic program. And then I will tell you about the different tools that we have developed, or let's say refactored, in order to enable these goals. So these are the masking tools, the Zorro and SkyKatana, and a couple of counting tools, Gundam, which is a code we had before, and we sort of refreshed it, and Corrgi, which is a new development within the frameworks of LSDB and HipScat. And I will show you some example workflow of how do you compute correlations with these, some preliminary results, and some prospects projects for the future. So first, as you know, galaxies are not randomly distributed in the sky. So the probability of having two galaxies in a given volume is, of course, proportional to that volume, and is, of course, proportional to the density of your sample. But it's also proportional to a term here that we have coined as the correlation function. So the two-point correlation function quantifies the excess probability relative to a random distribution of finding pairs of galaxies or objects in a more broad sense. Let's talk about focus on galaxies here, separated by a given distance. And you can estimate these distances in different geometries. You can, for example, work in angular geometry, and you calculate the angular correlation function, W theta, which is essentially the number of pairs, galaxy, or data separated an angle theta in the sky, divided by the number of pairs separated the same angle theta, but that you will count in a sample that is completely randomly distributed. So this is the correlation. It's a very simple definition and a very intuitive definition of what is the correlation function. As I said, you can work in angular space, but you can also work, if you're lucky enough, and you know the distances between your galaxies, you can also work out in real space. So you can estimate psi of r, which is the excess number of pairs separated at distance r between the galaxies, divided by the expected number of pairs at the same separation. So here is the geometrical cartoon of this. You have two galaxies here separated in a distance r, separated an angle theta. And if you are sort of poor and you don't know the real distances to galaxies, which is almost always the case, you can work out the projected correlation function. And the projected correlation function, what you do is to decompose the distance between two galaxies in two directions, one perpendicular, one, let's say, within the plane of the sky. So this is a projected direction, and one perpendicular to it, or radial, which is a bidirection. And in this way, you can work out a correlation function that is a function of actually two variables. So it's a two-dimensional function. What you can do later is to integrate this correlation along the line of sight, so between 0 and some fiducial limit along the radial distance. And in this way, you get WP. And WP is the projected correlation function, which, well, I'm not going into the details of correlations, and so that I don't take my time, but it is a very useful statistical tool to analyze the clustering of objects in the universe. There are plenty of other estimators. These are the so-called natural estimators, but you also have, for example, the Hamilton estimator or the LINCC estimators, which involves not only DD counts or RR counts, but also cross counts between the two samples, so a real galaxy sample and a random galaxy sample. More important, what can you learn from correlation function? Well, in one word, you can learn everything. If everything means measuring the universe large-scale structure, constrained cosmological models, inferred cosmological parameters, baryon acoustic oscillation, constrained galaxy evolution, unification models, dark matter distribution, lensing, etc., etc., etc. So it's a bit exaggerated. It's not everything, but it's the more accurate answer will be a lot. And here I show you an example. This is the projected correlation function as function of the projected radius, of course. These are cross correlations between two samples. Low excitation radio galaxies, so galaxies that do not have low excitation lines, a bunch of low excitation lines in their optical spectra, and those that do have high excitation lines. And you can immediately see here, for example, in this green curve here, corresponding to the low excitation population, you can immediately see two bumps, this bump here and this bump here. And this corresponds to pairs, so counts of galaxy pairs that are actually within the same dark matter halo, because this is called the so-called one halo term. And at large scales, you can very easily appreciate here that you are counting galaxy pairs that are located in different dark matter halos. You can also appreciate that the low excitation population is more highly clustered here at all scales than the high excitation population. And this is sort of, I mean, you can contrast this with models that tells you that in the framework of AGN unification, these two populations should inhabit the same environments. And this difference here, especially at large scales, tells you that this is not the case. And there are models that actually point to different physics between these objects. I mean, real physics, real accretion physics. It is thought that the low excitation population is accreting hot gas in this advection-dominated regime, while the high excitation population accretes more in a more standard cold gas accretion disk. So this is an example to show you how we go from correlations at very large scales here to models of the populations of the objects involved to actual physical differences in the accretion modes, in this case, around black holes. This is just one example. So how do we matter about this? So we need to find a way to describe the exact area or the volume occupied by a set of galaxies, and we need to generate the random points over it. And then you would plug in your favorite recipe for the radial path. That's another story. You also need to work with very large samples, because to reduce the shot noise and prove the smallest case, you need a lot of random, usually 10 to 20 times more than your data sample. So an innocent computation of the correlation function is two loops nested in on each other. And for each y and j galaxy, you calculate the distance in some geometry, and then you pin that distance. So this computation, of course, scales as n squared. And if this computation involves trigonometric functions, you know trigonometric functions are very expensive to calculate, so you're in problems. So you usually employ data structures such as KD trees or linked list in order to accelerate discounting, so diminish the number of objects you want to estimate distance and actually accelerate the counting. So the data set that we chose to work with is a hypersupreme super strategic program survey. You know, this is a collaboration between Japan, Taiwan, and Princeton. This is a 3-layer, 5-band photometric redshifts and photometric survey, which is carried out in an 8-meter telescope, the 8.2-meter Subaru telescope. So on the wide layer, you have about 1,400 square degrees of area, which reach around 26 magnitudes and about 500 million objects. You also have the deep and ultra deep, which are smaller fields, much smaller fields, and which go 1 and 2 magnitude deeper. And these fields are chosen to overlap the Sloan Digital Sky Survey, essentially for purposes of photometric and astrometric calibration. And you have a lot of information from other surveys across the entire electromagnetic spectrum. You have ACT, cosmology, and radio. You have infrared, you have X-ray with XMM and Rosita. So it is a very, very nice precursor data set that really looks like it's the closest we are to LSST data that we will start getting next year. On the sky, LSST occupies this many regions in the sky, so it's not the nicest survey to plot in the sky. But essentially, the latest data release adds about 600 square degrees of multicolor data, which is served by the NSQL database. And there are several evaluated data products associated with HSC. Some of them are photometric redshifts, and there are many versions of photometric redshift. You have, for example, the DEMP, which essentially takes the nearest neighbors of galaxies in the color magnitude space and fits a polynomial to it in order to infer the photometric redshift of galaxies. You also have the Mizuki, which essentially takes a different approach, which does a fitting of templates with Bayesian priors in order to get photometric redshift and physical properties of galaxies. You also have a few machine learning catalogs of photometric redshifts, and there are a couple of other ones. For this work, we have chosen to work with the damp photometric redshifts because essentially these are the ones that have the smallest error or the best error behavior. And as you also might know or might be aware, an 8-meter telescope, bright stars can cause, I would say, severe artifacts or effects on galaxy identification, photometry, lensing, even cause, entire holes in the survey area, artifacts, and so on. So when you have a bright galaxy here, you see, for example, a halo around it. Sorry. You see a halo around it. You also have these ghost images caused by internal reflections in the camera. You also have, of course, the blooming effect. So the electrons, the CCD wells get saturated by electrons and they start to spill around a column. So you get these spillings in the horizontal direction. And you also have issues with the subtraction of the sky around these objects. So sometimes the sky is over-subtracted, and for example, in regions around here, you have an artificial deficit of sources caused by background over-subtraction. And this is called the deep area or the deep effect. So what we have compiled during our incubator with a local data set for HSC. So we successfully downloaded the HSC data per band catalogs, and these are several 100,000 files. So that's what I say successfully, because it was not easy due to connectivity or storage issues. Gostiet put a lot of effort in working with this. We have also successfully downloaded the DEMP photometric redshift catalogs, as well the full photometric redshift distributions for using in the future. We also have HSC fluxes. We also have all the HSC columns and fluxes for sure. We also have C-model magnitudes for galaxies that have photometric redshifts. We have also successfully got our list of bright stars and their horizontal boxes that were employed to build the HSC mask. So this is a list of about 3.5 million stars that will be the seed of the masking procedure that I will tell you in a minute. So this is the local data set that we compiled in Carnegie Mellon. And this is what we use to actually find out what areas of the sky this data set occupies. So for that, you need a tool, and you have two approaches. You can either go through pixelization, so you divide the sky in a bunch of pixels that you know where they are, you know what shape they are, you know the properties, you know they have equal area, they have sort of regular shape, they are hierarchical, they also have these isolatitude properties. And you know these pixels, depending on the order of the resolution we work, you can get an approximate coincidence with the area that you're trying to describe. You also have the option of working with an analytical approach. For example, using Mangle. Mangle describes these areas in terms of spherical polygons. These can be, of course, numerically expensive, but the benefit that you have is that you have an exact match with the area that you're trying to describe. So you will say that you have a JPEG, a JPG picture of the sky with this approach, and you will have sort of an SVG picture of the sky with this approach. So we chose to go with the pixelization approach for sort of obvious reasons. And the first result is a package that we called Zorro. Zorro, I don't know if you're aware, but this is a character from a TV series from the late 80s, I would say. It is very popular in Latin. It was very popular in Latin America. Actually, the actor of El Zorro lived many years in Argentina, I think. And the idea is that you cut areas of the sky. This is why you have a sword, a knight, and a mask. So how does a Zorro works? Essentially, what it does is start from a list of pixelated areas of, these are essentially circular areas marked by stars and their horizontal boxes. And you group them by their location, not not at a higher order, but at tiles at the small order. So that is called a split order, which is low, usually at around 5 or 6, something like that. Then you create a coverage map from a point source catalog, for example, the galaxies in HSC, with a certain coverage order. And you define what your mask values will be. So what will you store in this mask? So this values column is our mask. And for objects within the coverage, you say it is either 1 or 0, so you set the first bit. And if the pixel is within the deep region, you set the second bit. And if you have a star or a box affecting a pixel, you set its third bit. And what the Zorro does is then working from the bottom up. If you have 4 children leaves in the helpix tree that have the same value, for example, they are affected by the dip, they are merged into a single higher order pixel or parent pixel. And this is what we call the multi-order continuous map. Then you had to import this multi-order map using a high pixel threshold. And then once this is done, you can query this multi-order map like any other head scheduler. For example, you can run query and give me all the pixels that have a value equal 13. And here is your list of pixels that are different orders. So order 17, 16, and whatever you have here, all these pixels have the value 13, for example, describing objects that have affected by the bright star. And then what you can do is to join this with any other point source catalog. So you load your catalog and you merge as of your mask with this catalog. And then you can query your catalog and, for example, give me all the objects actually that are affected or that are inside a pixel with value 13, for example, a bright star. And in this way, you have translated your mask information that you have into your multi-order map into the source catalog. So you can, for example, filter these objects, these sources. How does it look this in the sky? Well, this is a mask for a region, a piece of HSC. You can clearly see here the bright stars, the horizontal boxes, real. And this, you can, I mean, it's hard to plot these masks, but these are not empty pixels. These are just higher order pixels that are higher order, so that they look like empty. But these are not empty regions. So all this is, most of this is actually covered. Maybe it's better to look at them here. Here you can see a zoom of the previous mask. So you can see you have a very bright star here, its box, and smaller stars here. So all these, this is a deep region of the stars. You have an inner radius and an outer radius. And these are the higher order pixels that looked empty in our previous slide, but these are not empty. This is just a very nice representation of the mask. Performance-wise, the Zorro is very fast. It can work out the entire HSC mask in around 6 minutes, working in a single node in Bridge 2. That's 128 cores, so that's not bad at all. But our hero had a split personality. So in the TV series, El Zorro was also a knight with a sword, that sort of a Robin Hood, defending the poor people, but He also was Diego de la Vega, which has this, let's say, daytime character. And it will have been a perfect, let's say, analogy for making another software. But calling a software Diego de la Vega is a terrible idea. So we came up with the SkyKatana. SkyKatana is a package that we developed to manipulate the spatial mask on the celestial field in sort of a pipeline way. So the idea is that you create stages, and these stages are nothing else than Hellspar's pixel maps that accounts for various effects. For example, regions around bright stars, regions of low depth, regions of bad seeing, regions affected by extended sources, and so on. So SkyKatana is public, it's available, and it's pip installed, so you can start working with it right now, if you wish. For those that you are unaware or do not know Hellspars, Hellspars is a sparse implementation of Hellpix in Python. Essentially, it implements two Hellpix maps. One, like here in yellow, works at a coarse resolution, so you have very low orders here, for those usually typically from 4 to 8. And this is your data sample. But it also brings along another high resolution map called sparse map, which of course is high resolution, orders usually 12 to 29. And this high resolution map is built and tracked and stored only for the pixels that have contained data in your coverage map. So in this way, you can avoid storing full sky maps at higher resolution. So you save memory, you save storage, and you save CPU time. And this is important and sometimes imperative, because even at order 15, so n side is 2 to the 15, and you have around 10 to the 10 pixels to provide a geometrical description of the full sky at around 6 arc-second resolution. So we don't want to be dealing with 10 to the 10 pixels to describe maybe a small area like HSC, a smaller area like HSC. So this is why Hellspars is really, really nice to work with, and we adopted it for SkyKatana. So once you use SkyKatana to create these stages, you can intersect this with mask from external service. If you have another one, you can combine all these stages into a final mask, and you can visualize these stages. As I said, it's not easy to visualize masks. You can also overlay bright stars and shapes, and you can generate random points over any stage of your pipeline, of your mask pipeline. Finally, you can apply this mask to a catalog. So that is essentially, give me all the sources inside, and please take out all the sources that do not fall inside. So let me here show you quickly how this works. So we're gonna go. So the size of the font is okay here, of the text. Can you read it?
Yes.
Okay, thank you. So this is a quick introduction notebook. Essentially, I'm gonna go very fast through this. So essentially, you define you have your catalog of data. This is just a piece of HSC. So this is a mini spring, a mini spring HSC. So a very small piece of around 50, it's like 60 square degrees of HSC. You have your list of stars and your regions that are the circular regions around stars and the horizontal boxes around them. You also have to input a patch file, which is a list of patches in the case of HSC that tells you that have quality assurance measurements, for example, you know the depth of this path, you know the seeing of this path, you know the number of objects detected in each of these paths. You can also input a list of, for example, elliptical regions, which you will use to mask your extended sources. I will talk to you about this in a minute. And you can also input your list of user-defined regions. So from any other surveys, you can input your circular pointers, your quadrangular polygon regions. And how do you use this? It's very simple. You just instantiate your sky mask pipe object, and you want a resolution output of order 15, let's say. And then you just create all the stages that you want. You build your footprint stage, so that is essentially pixelizing your input data. You then pixelize your patches. In these patches, you can filter by any of the properties that you have in your patches. Then you create your holes mask. By holes, I mean regions that you want to excise from your analysis. Those are the bright star, the regions around bright stars. And you can, if you want, build your stage that takes into account the extended sources. Sometimes the galaxies, nearby galaxies, are shredded into multiple sources, and these can cause biases in the counting, and you don't want these areas. And finally, you can combine all this into a final mask. So you see, you start from 65 square degrees in your footprint. You have 54 square degrees on your patches. You have 16 degrees in your bright stars. You have a half a degree on your extended sources, elliptical sources. And when you combine everything, you have around 43 square degrees in the end. And this runs very, very fast. You can plot here, for example, this is the footprint. This is a small piece of HSC. Or you can plot actually another stage, which is the mask. The mask is actually the final mask, combined mask. So this one doesn't have all these patches here around, has all the bright stars carved inside. Maybe it's better to make a zoom here. You can make easily a zoom plot here, and you can actually overplot the areas that you have excised from your mask. So the bright star here. And you can see there are many, many, many bright stars. So all these things create a hole in your mask. You can also plot, in this plot, I plot random sources within the mask, but you can also plot your real sources. So you can actually see, for example, here, the sources that you will be discarding by applying the bright star mask in this case. You can also compare, and here you see the footprint, the sources as they see in a region of the skies. And on the right, you plot the mask stage, which is the final mask. So you have gotten rid of all these areas here, and you have gotten rid of all these areas around bright stars. And then you can generate random. For that, you just use a simple function, make runs on any given stage and the number of randoms that you want. And there it is. And you can apply your catalog. So you read any catalog, for example, your input catalog. Here, I read a HSC catalog. And I just say apply a given stage of the mask. And you see, you end up with around 5 million sources within the mask. You can also save this pipeline to disk if you want. Another feature is that you can add a user-defined mask. By user-defined, I mean another survey. And for the purposes of illustration, another survey here is just a bunch of circles and polygons. You see, I just build a user-defined mask. and I can recombine the final mask. And this is what you see, the happy smiley face on the sky. And you can also apply, for the case of HSC, custom HSC patch filtering. So when you build your footprint mask and then you build your patch mask, you can filter these patches by any property that you want in the patch. For example, I only want patches that have a minimum depth of 26.3 in a given band. So you can, for example, see here what happens when you don't apply this cat and when you apply this cat. And you can, in this way, you can create very complex masks with very little effort. So let me give you some more options that SkyKatana offers. Here, for example, you can see the effect of pixelizing at different resolutions, 18, 13, and 16, and you can compare how your mask looks at different resolutions. You can also, sometimes when you pixelate at a certain order, you end up with small holes in your survey. So these are small single pixel holes that you don't want to excise, at least not in the beginning from your survey. This is just because of the pixelization order, so you don't find any sources here. Or you might have a small bright star inside. So there is an option to remove these isolated empty pixels. If you apply these options, then you end up with your continuous area covered. And sometimes, especially in HSC, we have seen that differential coverage in different bands creates this kind of structures that essentially are caused by the lack of coverage in a given band. For our purposes, we wanted to include all, the area covered by all bands. So, for example, the Y on the or the C band has not been observed here. This is the cause of this hole. So when you pixelize this, sometimes this hole there will be mismatch between your mask and your actual data in the border regions of this hole. So there is an option, erode borders, that you get rid of you turn off all the pixel borders here. So you essentially enlarge your hole, but in that way, you make sure that your data and your random samples will match much more better. Of course, it has the effect of enlarging these single isolated pixels that you sometimes find. So the best way of dealing with this is first removing the isolated pixel and then eroding the mask. So in this way, you only end up with the hole, the big hole here in your survey mask. And finally, another option is to create patch maps. And for example, for HSC, this region here that you see around the edges here, of course, it has been observed less times, is less deep than the inner part. And just by filtering by patches, you can create a mask that isolates this region and excites them from your survey. So this is very nice in order to get a more uniform coverage like here. Okay. And I'm going to go here for extended sources. You have the effect that sometimes, as I said, these extended galaxies, usually an arc minute or something like that, they get shredded into multiple sources. So you want to excise these areas. So what we did is these are the pixel examples of the pixel areas covered by this. So what we did is to take a catalog of the extended sources up to 50 megaparsecs, and we pixelized the ellipses that are listed in that catalog. And in this way, you can excise this catalog or any other catalog of extended sources in using SkyKatana. So, okay, let me go back to the talk. All right, here we were. How do we count? Essentially, what we do is we had a code which is called Gundam. Essentially, it allows you to calculate correlation function. It has lots of optimization for speed. And the work from the LINCC team has been to rehydrate this code to modern standard. This is a very good effort especially from Sandro. So now Gundam is pip installable and can run anywhere, even a vacuum cleaner. That didn't happen before. So we are very grateful for that. Gundam works in 4 steps, so there are 4 steps to acceleration. Gundam uses linked list and skip list in order to improve the performance of the counting. I won't go into the details here because I don't have time for this. It also uses Fortran because Fortran, as you know, is a very fast language to do scientific computations. And it also uses very optimized, highly optimized loops. And these optimizations include reverse looping, early stopping, unrolling iterations of the loops, watching out the nesting order of these loops. So the last, let's say, weapon of Gundam is the parallelization. Gundam uses MPI and OpenMP for parallelization, so it runs multi-thread and multi-processes. But as I said, the idea is to make something that can run full sky with LSST scale. So it came out as a Corrgi. Corrgi is a code that essentially does the same thing. It computes correlation functions, taking 2 steps from Gundam: the Fortran codes and the loops, which are in Fortran. So we took these 2 optimizations and tried to insert them into HADS and LSDB framework. So given a region of the sky, HADS and LSDB are very efficient or very straightforward to find which partitions they cover. And it's also natural to distribute the analysis. The analysis is the computation of the pairs between 2 catalogs, the left and the right, or the data and the random samples. And what you do then, the analysis is histogramming, essentially counting how many are as a function of distance in a certain radius. So the initial approach was promising, worked very well. But unfortunately, as we came up with larger and larger computations, we realized that the graph was too large, sometimes too large to compute, or we had the similar run times, and we have memory leaks maybe. This is probably related with task rather than heads. File system issues, we're not sure about that. So Sandro started implementing a MapReduce strategy so that this graph actually gets shredded into smaller chunks. It's the computations are done partially and stored to disk in partial way. So then they are shuffled so that you can add them together in the right way, and they are reduced, so they are added at the end. So they are essentially intervening the computation of this large acyclic graph. How do you do that? Well, you have to ingest your catalog samples, for example, HSC galaxies. So this is just importing a traditional HIPSCAT catalog. For this example, you have 2 million galaxies and 8 million randoms. redshift between 0.55 and 0.95, essentially the same area that we saw before. Then you import from Corrgi your angular correlation. Here are the catalogs, your data catalog and your random catalog that you have built using SkyKatana. You create your parameter dictionary, let's say it's a dictionary, where you specify the number of pins, the separation of the pins, the size of the pins, and which estimator you want for the correlation. Once you do that, you just compute your autocorrelation. In this case, it's the angular autocorrelation. And here you see the plan, the map reduce strategy working in place. And a few minutes later, you get this. So this is W theta. So this is the first angular correlation of HSC galaxies using Corrgi. So it looks very nice. This is a projected, these are many projected correlation functions. So this is WRP as function of RP for samples of galaxies divided in different apparent magnitude pins. So you have the brightest here on top, and you have the faintest here at the bottom. For this, we used Gundam because here I have used, I think, like 60 million galaxies and 100 and something million randoms, which Corrigi still cannot run, or at least I wasn't able to run it. Here you see the projected cross-correlation function. So this is to show you there are differences. So I take the sample, the subsample of massive galaxies. So masses 10 to the 11.3. This is the red correlation function. And then the least massive galaxies, which is this blue line here, and you see they separate as they should. So this is a very nice test. In terms of performance, well, for the angular part, you see Corrigi works more or less in line with Gundam, which is amazing considering that Corrigi is not using any sort of linked lists or any sort of KD trees or anything like that. So this is the real power of HipScat and LSDB. For the projected part, we are not there yet, as you see. So it's much slower to work with Corrigi. Then the projected correlation function is more or less the same. But they work. Actually, just a couple of days ago, I was able to reproduce one of these curves, projected cross-correlation functions, with Corrigi and without errors. So another actually more scientific application of this is the cross-correlation between quasars and HSC galaxy. So we took the Gaia unwise quasar catalog. This is the Gaia or Gaia quasars. These are quasar candidates selected from Gaia that have blue photometer, red photometer spectra. They have, let's say, relatively small errors. But the point here is that they cover a very large volume, and it's actually the largest volume for any spectroscopic quasar sample, about 1.3 million quasars. Of these quasars, about 30,000 are within our uniform coverage mask. We have around 60 million galaxies there as before. We have overlap in redshift space, which is essential for this. We see a small bimodality here. This is the R minus W1, so optical minus infrared color. And here we have the cross-correlation of two populations from there. This is the quasar galaxy cross-correlations between the obscured, or let's say more obscured quasars here on the right side of here, and the less obscured quasars here. I'm sorry. Less obscured quasars here. So we don't see any difference, which well, we have to interpret these results, even other results. we took a step further and we took actually this tail of the distribution here, and we cross-match also these tails of the distribution, so we get rid of everything in the middle. And we still see no difference between the clustering of these two quasar populations. This is sort of contradicting with the recent works from Rosado et al., which is just differences in HSC quasar candidates and LRG galaxies selected in HSC, but this is probably a result of a different selection. The point is that we have used the tools that we developed to actually get to start getting scientific results. We also have prospects. MALS is one of them. This MALS is the Mercat Absorption Line Survey. This is a set of 391 pointings, about 1 million radio sources, that is selected in order to trace the evolution of atomic and molecular gas in galaxies and their relation with star formation. So it will get lots of AGNs here, lots of AGN feedback physics, and thus obscured AGNs. Here in the background, you see the 391 masks of MALS, and we have run the intersection as an external survey. We have run the intersection with HSC. This is a sum of one of these pointings. Here you see one of these mild pointing, the bright stars carved by the HSC, and the patches that were discarded due to uniform coverage. So this is a very rich data set for this. We also have further science. We plan to use HSC and Gaia to detect and characterize stellar streams in the Milky Way halo and try to find its progenitors. That is essentially filtering the stars in order to find via isochrone filtering the stellar populations of these streams and its characteristics. And a study with Corrgi and Gundam, it's a spatial clustering. There's a spatial clustering to see if it can improve its identification. And finally, we also plan to release, to build and release a full half-sky LSST mask. Essentially, we will build on the results we learned from HSC and the DC2 simulated dataset, and also the images that we will probably have next year, real images taken by LSST. We include also systematic effects of, for example, galactic extinction and seeing and other property maps. And we add some features that are present in Zorro and SkyKatana that are present in these two packages, but they are not present in both. So thank you very much for your attention, and thank you very much to the team that made all these things possible. Melissa, Sandro, Kostya, Sean, Alex, Jeremy, Rachel, but also Andrew and Geno, and of course, my colleagues here in Argentina. Thank you very much.
Okay, thanks, Emilio. We have a few minutes for questions. Please ask questions in Slack, chat here on Zoom, or raise your hand if you have any questions. We have a question on chat from Bob. Bob, do you want to ask it? You can unmute yourself.
I was just saying it's appropriate that the actor who played Zorro was also the father in Lost in Space.
I'm sorry, say it again.
The actor that you show who played Zorro.
Yes.
He was also in the TV. He was in the TV series Lost in Space.
Oh, really?
It seemed very appropriate.
Yeah. Guy Pearce, I think. Guy Williams, sorry.
Okay, I have a very quick question. So could you say a little bit more on how these would scale when you have LSST data compared to HSC?
Well, that's a part that we still have to work with. We don't know. Sandra has put a lot of effort in trying to iron the quirks of task and trying to find out why sometimes computation stalls. I mean, sometimes even the hipscat import part fails. I have run into, for example, importing a 20 million random, trying to import a 20 million random sample, and hipscat complains it doesn't want to import it, no matter what I do. And I say, okay, this is too much memory or whatever, and I import another catalog, 14 million galaxies, and it goes without an issue. So those kind of things are sort of buffing, and when we have, it will take some time to find out. I don't know exactly how, when we will be able to scale these to LSST, billion objects. But this shows, I mean, these examples that I just showed, I think demonstrate that the principle works, and it works pretty well. We just have to iron the dependencies, particularly with task.
Okay, we are right at the hour, so let's thank Emilio again. Thank everyone for attending the Tech Talk. The next Tech Talk will be on November the 14th at 10 a.m. Pacific, and we'll be hearing from Tianqing Zhang about the LINCC Frameworks project Rail, a comprehensive photo-Z infrastructure for roving data. Please join the LSST LINCC Tech Talk channel and subscribe the mailing list for more information and future announcement. With speakers' permission, we'll post today's Tech Talk on our YouTube channel within the next few days. With that, let's thank speaker again, and thank you for your attendance. Have a nice day.
Thank you. Bye-bye.